So I'm going to talk to you about work that we've run over the last few years looking at flood early warning systems. So hopefully I'm going to echo a lot of the comments that Colin has found and look at the approach that we've taken within Indonesia. So this is a project that was joint between Bandung Institute of Technology in Java, ourselves here at Durham, quite a wide range of people at Durham, and also with the UK Centre for Ecology and Hydrology. Now, I'm going to take you to the case study that we've been working on in West Java. Bandung is here, Jakarta's just over here, and it's the town of Majalaya. And Majalaya is, I would say, fairly typical of many towns in this area. It's on an old lake bed, it's very low topography, lots of rice grown around that area. Also within that area, it's a combination of textile factories, residential and commercial. And this is a community which is facing flood risk. It's not facing flooding that's happening every year or every 5 years or every 10 years. It's happening multiple times a year, 3 or 4 times a year. So this is one of the people we met within the village who had a house that was very close to the river. And that was how deep the flooding was last time it came through. And there's lots of other communities that are living across Indonesia, these kind of bankside communities, these informal properties, which aren't getting information about, well, much information around any flood warning. There's no government system providing information. The local flood action group that we were working with in Majalaya, they set up a system where they're monitoring rainfall up in the catchment, getting that data through over the cell phone network, and that might give them 2 hours, an hour, 2 hours warning that a rainstorm has happened and that water could potentially be coming down. The other issue that we've come across by talking to people on the ground was that there's a lot of distrust of flood warnings. When this is an informal settlement, there has been cases where following a flood warning, the government has come in with bulldozers and cleared out those areas. So there's not necessarily a trust of the warnings that are coming through. So this really drove the research need for this project. So currently in Indonesia, but many other parts of the world as well, there's no central flood warning. Ones that have been put in place are giving hours notice, where actually if you need to move things out of a property or adapt what you're doing within a business, you need more time to warning that. And also the warnings are, there's a flood coming to this town, rather than it being personal to that person and to make your own decisions around what's happening to your property, your place of work, your routes. And as I said, the flood warnings might not be trusted. So we set out to put together a system that would address these problems. And it's a simple chain. Effectively, it's 5 boxes. All we need to do is take the weather forecast information. So NOAA publishes every 6 hours a 10-day weather forecast for the whole world. So we can take that information on future rainfall for the next 10 days. We need to convert that rainfall and temperatures into what the river's going to flow. We need to work out where that river water is going to go, and that will give us a flood map. And then we need to tell the community. So, simple. However, to get the catchment model to work, we need some extra information. As Colin was talking about, we need that local rainfall information. We need that local observations of the river flow. To do this detailed flood inundation mapping, to say, well, actually, your house is going to flood and yours isn't, we need very detailed topography. So we need a way to create that. And we need to understand how the community wants to receive these messages and what the balance is between the uncertainty in the messages and the time length, how far forwards in time you want to look at. So within the project, we are, would you believe we had a project impacted by COVID? And slightly delayed. We're up to this point, we're doing, Jessica Lehman in geography with the team is working on some workshops with the community to look at that communication side. So we've kind of gone through and addressed most of these problems up to this point. So in terms of getting some rainfall in, we've implemented a rain gauge network. We've got a combination here at the top there is the Met station, which measures the rainfall, the temperature, the wind speed. We've got a backup rain gauge here, and then this is the telemetry information to push that out. The one that we use most is via the cell phone network. This was experimenting with another kind of wireless communication network approach. So of these, we can get every hour the updated rainfall fed into the system. That then feeds into a catchment simulation model. That's taking in that observed rainfall for the last 100 days, and is then we can use that with the weather forecast data to predict the next 10 days. So generally speaking, I'm not going to talk you through every part of this. The key thing is we've got precipitation coming in at the top, and we've got river discharge coming out, and that enables us to make graphs like this, where we can go through and predict where the flood flows may be and what's happening. And this is a model that was built by Simon Mateus in engineering here in geography. He was the project PI for this. And generally, it works well. There's certain times when they don't match together so well, but that's kind of largely driven by some of the data we have, either in terms of the quality of the river flow or the quality of the weather data. So we can now predict the river flow into the community, and we can predict that 10 days out. The next step is to get it down so it's hyperlocal. So we're saying how individual houses, individual roads, individual workplaces may get flooded. And we're aiming to run this on basically a 1 metre grid resolution. That is better than any flood warning system that we have in the UK. Normally, we'll talk about an area of a town will be flooded, will be the warning that will be issued from our Environment Agency. So we're trying to build something which is that next level of detail. As I said, what you need for this is very detailed topographic data. And for England, the complete LiDAR data set, which is that detailed topography, was published this summer. For most parts of the world, we don't have it. So there's various approaches you can do to build this data set. You can build it off satellite data, which can be quite costly. The approach that we took within this project is working with drone data. So we kind of felt that most communities, if they're working with a university or working with a wider set of kind of supporting areas, maybe find that this type of technology is accessible. And by mapping out with a drone and processing that data through, you can build this detailed topography. But the blocker on this is going to be the training. People can get the drone, but what do you do with it? How do you actually process the data? So we ran a workshop at ITB with both the Flood Action Group, the local community, students and faculty at the university around how do you fly the drone. There's the one just up in there. It's kind of hidden in the text slightly. And we took them through not just how do you process data, but how do you fly it, what's the safety implications, how do you actually get this to run it out. ITB then went out across this community and did the mapping, and this is just a little subset of the data of the 3D model. And off this, we can start to map out where's flats, the detail of the fields, where the houses are. And off this type of data, we can then go through and build a surface model. So this is, again, a little snapshot of the surface model. We've got a data point every 13 centimetres across there. We can see all the buildings, we can see the fields. These kind of little holes here are where trees are. Once we've gone through and done some extra processing on this data, we can then feed that in to the flood inundation models. So all we need to do is take our river flows we had earlier, drop them in to the top of the river here. The 2D hydraulic model will work out where that water goes, and we've got a flood map. Easy. You can tell that I'm halfway through my talk. There's going to be a problem. There's going to be a but. The but is that for the future, making predictions of the future is tricky. NOAA gives us 21 possible futures from their weather forecast data. From the rainfall runoff model, we have 30 different parameter sets, which are slightly different ways to conceptualize that system. And we need to run all of these weather series for all those parameter sets. That gives us 630 possible river inflows and 630 inundation maps. And that gives us a kind of question, as I said, around that uncertainty of when do we start telling people. Now, you could say, well, you've got 630, just take the best one, work with that. We don't know which is the best one. They're all equally plausible versions of what the future may be. If our flood model takes a couple of hours to run, to crank through those 630 different river flows, it's going to be 51 days of one computer to process that. And these weather forecasts are updated every 6 hours. And we end up with this problem. So we need to be a bit smarter. The approach we've taken is rather than going through and building and actually running the full physics hydraulic model, we're aiming to build a statistical emulator of that model, or we have built a statistical emulator of that model. So here is just 3 snapshots of different inflows from 50 cubic meters per second up to 250. And if we take a single point as an example, we can say that actually, as the river inflow increases, the predicted depth at that location increases. And if we go through and fit a statistical model to that, so in this case, it's a polynomial fit, which relates the river inflow rate to the flood depth. Rather than running the whole model, which takes hours, we can use these equations for all 30,000 locations across the area and make those predictions really quickly. So we can get the warnings out in a timely way and also in a low computational cost way, which means it's easier for the community to fix. To get this on to the next stage, working with colleagues here, we've gone through and built an online web application for this. So this is for a theoretical flood happening the next day. What it gives you is the very detailed floods of where they are, what's their probability are. Users can go into this, create an account, say, look, this is the point I'm interested in, send me an SMS message when it gets to a certain flood warning level. We're going to move this on soon so we can actually go through and send WhatsApp messages as well. And we've explored various other ideas of how to get those warnings out, not just through mobile phones, but by more kind of passive approaches and other ideas, which I haven't got time to talk about. So in terms of next steps, the open source software stack is being built. We're making it easy for other people to pick this up and run with it. We're testing it out with the community in Indonesia, and we're looking for other locations where it would be good to apply this and test it. My general approach is when you've built something, is take it somewhere else and break it, because that's how you learn. And we can looking to apply it to other places. So in summary, this flood early warning system is designed to be an open source, community implementable flood early warning system, but doing things at a very fine spatial resolution. And we're building up the training and documentation so that people can take it and run it without having to have a dependence back to ourselves. So any questions from the room or online?
If I go back to your model description of predicted versus data, I have the feeling that your parameterization has a lot to learn still. Yes. How do you continuously update your model? Or let me phrase it differently. When you do your predictions, I think you want to attach some level of confidence in your prediction, and I think the best estimator for the confidence of future prediction is how they a posteriori describe the past. So do you have some kind of quality of my parametrization based on that plot, and that you're continuously refining it such that you run, say, of the order of 500 sets that over time become better and better. Is that the plan, or do you shock freeze it in GitHub and wish everyone luck?
So in terms of this data, we don't have a live update of river flow. The vision is exactly what you're talking about there. So you're measuring the rainfall in the field and the river flow, and that is dynamically updating that ensemble of fit parameter sets. So that's one of the things for the future work. As it stands, there's quite a long lag with getting data out of Indonesia. So what we would like to be able to do as an interim step is get it so you can just upload more data and it will then refit the model. The problem is with a lot of this, the rainfall data is, the river level. Yeah, so. Well, no, it's because say that the amount of sediment coming in, the same was kind of talking about with the canal, the amount of coarse sediment coming in there, the cross section's changing. So you might have the depth, the height of the water, but you don't know where the bed is. So you've got a lot of uncertainties in that measured data. Yeah. Any other questions?
I think it's a comment, and we might end up discussing this later. I've been working with early warning systems and modeling similar to this, and one of the things we're finding is just the word early warning I'm a bit uncomfortable with. And we tend to use early forecasting and then with the communities talk with them about what that forecast might mean in terms of warning. And I know it's semantics, but it actually is making a big difference in how those communities are viewing. The other thing is the word prediction. I'm always uncomfortable with the word prediction, and so tend to use something else like, forecasting or probabilistic forecasting or something like that. Just because the prediction often to policymakers means, you're going to tell us the day, the time, and it kind of comes back to what we're saying here from Frank, which is, well, how confident are you? And this gives you a little bit of leeway. I mean, we could talk about that more, because I know practical action, you've been dealing with this also, and just the semantics on how we give these.
Yeah, thank you. It's the exact set of issues, which is the next stage of the project. We've got to the point where we've got multiple days and a distribution of potential flood depth for every location. But how is that communicated? And the words matter, the visualizations matter. This is the example I showed earlier. That was my we need something to work to as a Aunt Sally to show the community, and that's where we're at now. And I'm afraid I'm going to have to cut myself off there.